7 types of EV motors. When we talk about electric vehicles, everyone obsesses over the battery, range, charging speed, lithium-ion versus solid state. But what about the actual heart of the machine? The motor. Most people think EV motors are just giant slot car engines. But did you know automakers use 7 completely different motor technologies to power everything from budget commuter cars to multi-million-dollar hypercars? Today, we are tearing apart the powertrain to look at all 7 types of EV motors, how they work, and the massive pros and cons of each. Let's dive in. Number 1. The brushed DC motor. This is the absolute grandfather of electric propulsion, historically used in early electric vehicle conversions and older transit systems. It works by using physical carbon brushes to mechanically transfer electricity to the spinning core of the motor. The big pros: it is incredibly simple, requires no advanced electronic controller to operate, and provides maximum torque right from 0 RPM. The big cons: physical brushes create friction, generate high heat, and wear out over time, making maintenance expensive. Because of this low efficiency and bulky structure, you won't find brushed DC motors in modern production electric cars. Number 2. The brushless DC motor, or BLDC. As the name suggests, engineers fixed the previous motor's biggest flaw by removing the physical brushes entirely. Instead, it utilizes an electronic commutator or controller to dynamically redirect electrical current to spin the rotor. The big pros: lower maintenance, an improved power-to-weight ratio, and highly reliable longevity. The big cons: it requires complex electronic controllers to manage the switching, which drives up production costs. While less common in high-performance highway cars today, BLDCs are widely popular in electric scooters, e-bikes, and smaller light-duty EVs. Number 3. The 3-phase AC induction motor, also known as the synchronous motor. Fun fact: this is the exact technology invented by Nikola Tesla way back in 1887. It works by feeding alternating current into the outer stationary coils, called the stator, to create a rotating magnetic field. This spinning field induces an electrical current in the inner rotor, causing it to chase the field to create torque. The big pros: it is incredibly robust, cheap to manufacture, and doesn't require a single rare earth magnet. The big cons: the rotor can run hot and suffers from lower efficiency during slow, stop-and-go city traffic. Tesla famously relied on induction motors for its early Model S and Model X, and Audi uses them heavily on the front axle of its dual-motor e-tron SUVs. Number 4. The permanent magnet synchronous motor, or PMSM. This is currently the undisputed king of the modern EV market. Instead of waiting for a magnetic field to be induced in the rotor, a PMSM features powerful, permanent neodymium magnets physically embedded directly into the rotor. The moment electricity hits the stator, the rotor instantly locks onto that magnetic field and spins perfectly in sync. The big pros: unmatched power efficiency, a highly compact size, and that instant push you back in your seat acceleration. The big cons: those permanent magnets rely heavily on rare earth materials like neodymium and dysprosium, which are highly expensive, geopolitically risky, and environmentally damaging to mine. Almost everyone uses this tech, including the Nissan Leaf, Porsche Taycan, Hyundai Ioniq 5, and the primary driving axles of Tesla vehicles. Number 5. The externally excited synchronous motor, or wound rotor motor. This was invented to give automakers the high efficiency of a synchronous motor without the environmental guilt or high cost of rare earth magnets. Instead of using raw magnets, engineers wrap copper wires around the rotor. By feeding a small amount of DC electricity directly into those rotor coils, it transforms into an active electromagnet. The big pros: zero rare earth magnets, cheaper raw materials, and great energy efficiency when cruising at high highway speeds. The big cons: the physical slip rings used to feed power to a rapidly spinning rotor add physical complexity and make the motor housing slightly larger and heavier. BMW is the absolute champion of this technology, utilizing magnet-free wound rotor motors across their entire current Generation 5 EV lineup, including the i4 and iX. Number 6. The switched reluctance motor, or SRM. This is a completely different beast because it does away with both copper coils on the rotor and permanent magnets. Instead, it features a solid steel rotor with magnetic teeth. The stator windings turn on and off in sequence, pulling the steel rotor teeth forward by minimizing magnetic resistance, a property known as reluctance. The big pros: it is shockingly robust, has an incredibly long lifespan, can tolerate extreme heat, and is highly cost-effective to manufacture. The big cons: controlling the switching requires incredibly complex software algorithms, and these motors suffer from high acoustic noise and structural vibration, known as torque ripple. Because they are so rugged but loud, they are mostly used in heavy industrial vehicles, large electric trucks, and mining equipment. Number 7. The synchronous reluctance motor, or SYNRM. This is an advanced evolution of the switched reluctance motor. Instead of relying purely on a steel rotor, a SYNRM uses a specially geometric rotor design with internal air pockets that precisely direct the magnetic flux lines. Many modern automakers actually insert tiny, highly efficient permanent magnets into these air slots to create an incredibly advanced hybrid motor. The big pros: it delivers incredible efficiency across a massive range of speeds while using a fraction of the rare earth magnets found in traditional motors. The big cons: they are mathematically complex to design and require highly specialized manufacturing equipment to cut the intricate rotor profiles. Tesla famously engineered a variation of this hybrid SYNRM technology for the rear motor of the Model 3 to dramatically improve its highway range. Now that you know all 7 individual motor designs, how do car companies mix and match them? You've probably seen badges like AWD, dual motor, or tri-motor on the back of modern EVs. Instead of using two identical motors for all-wheel drive, genius engineers actively blend these technologies. For example, Tesla frequently pairs a permanent magnet synchronous reluctance motor on the rear axle for continuous daily efficiency, with a traditional induction motor on the front axle. Why do they do this? Because induction motors don't have permanent magnets, the front motor can completely power down and spin freely without causing any magnetic drag when you are just cruising on the highway. The split second you smash the accelerator or the wheels slip on ice, the vehicle computer wakes up that front induction motor in milliseconds to give you a massive boost of all-wheel drive power. So, which motor strategy reigns supreme? There isn't one single winner. If you want low cost, it's induction. If you want city efficiency, it's a permanent magnet. If you want a sustainable supply chain, it's a wound rotor. And if you want rugged industrial power, it's reluctance. Which of these 7 motor technologies would you want powering your driveway? Let me know in the comments below. Don't forget to hit that like button, subscribe for more deep dives into the future of automotive engineering, and I'll see you in the next video.